So we shift our attention to Argon modulation. And in Argon modulation, we have two types, phase modulation and frequency modulation. And we will see shortly what this entails. Assume you have a message signal as illustrated by MT here. Then, and the carrier is high frequency carrier in comparison to the frequency of the message MT. What we saw in amplitude modulation is that the amplitude of the carrier was changing, as you can see, with the amplitude of your message signal. And that is how we did that. We dealt with, and therefore we were able to apply an envelope detector to observe or to detect the changes in amplitude of the carrier, and therefore detect the original message. But now with the Argon modulation, we have two formats. One is that for the FM, we see that for high positive cycle of the message, we have high frequency component. And for the negative cycle of the message signal, we have a low frequency component. And therefore, again, we are able to detect if we apply, we transmit this message, then we're able to detect it, not directly from the envelope now, but with the varying frequency components. And similarly, we are able to modulate the message with different phases. And again, for the negative component, we apply some different phase angle to the carrier, and for the positive going portion, we apply a different value of the phase angle. And therefore, again, when we transmit this message, we are able to receive the original message signal before modulation. And therefore, having done that introduction, we can say that in amplitude modulation, the spectrum of the message signal is essentially the translated message spectrum. And the translated message spectrum, I've just brought it here in this diagram, just to illustrate the concept of the spectrum of DSB modulated signal. And therefore, what this means is that if this was the message, this is the spectrum of the carrier before it has been modulated by the message signal, then after the carrier has been modulated, it is going to be translated. This is the idea of translation, that we are going to have two sidebars, one on the upper and the other one on the lower side. And therefore, we are saying that we can directly see that there is a direct relationship between the spectral characteristics of the Argon amplitude modulated signal from that of the carrier to that of the translated after modulation due to the message. And therefore, from that example, we can always see that the bandwidth often never exceeds twice the message bandwidth. As you can see, we have seen the message bandwidth is omega m, and that of the carrier was centered at omega c, and therefore you'll always see that the upper side band and the lower side band is always either minus omega c minus omega m, and omega c plus omega m, and therefore that the spectral or the bandwidth of the modulated signal in AM it never exceeds the twice the message bandwidth. But on the other hand, for the Argon modulation, the spectral components of the modulated wave are not always related in such a simple manner, and therefore you're going to see some complexity involved in the message spectrum, which we will see in the subsequent sections. We also observe that superposition does not apply and this will be illustrated in problem 4.4. And the bandwidth of the Argon modulated signal is usually much greater than the twice the message bandwidth. So it will be much greater than this. But then there are some advantages that we shall receive from that. And one of them is that there is some improved performance in the face of noise and interference. And now to see how we were representing the amplitude modulated wave, which was represented in equation 3.1. I have written it right here. And what this meant was we said that the amplitude of the carrier, remember this is the equation of the carrier, the amplitude of the carrier was directly related to the amplitude with the message. So we could have a constant k there, and we say that a of t is directly related to the message signal. But now in this case, for the Argon modulation, we say that, and okay, just before we go to the Argon modulation, we say that in the amplitude modulation, we normally keep the phase or the frequency and the phase constant. But now, for the Argon modulation, we now keep the amplitude and the frequency constant. These are kept constant, whereas we change the phase of the phase angle of the carrier with respect to the message signal MT. And we'll see two different ways in which the phi of t can change. Therefore, we are saying that we can write equation 4.1 into 4.2, in which case we are saying that the theta of t is a function of omega of t, which is the carrier frequency, and the phi of t, where the phi is the phase angle of the message. And of course, that is written in equation 4.3. And then from that point, we can define the instantaneous radiant frequency x of t, which is denoted by omega I. And we see that omega I is always going to be given by the instantaneous of linear equation is normally given by the first derivative, who as expressed in equation 4.4. And when you, sorry, this is supposed to be the theta. And therefore, when you differentiate this this equation with respect to time, you're going to get this one as a constant, as you can see in equation 4.4, and the derivative of phi of t again, as can be seen right there. And therefore, we note that the phi of t is going to be constant. We're saying that when phi of t is constant, then the instantaneous radiant frequency will be given by the angular frequency of the carrier. And then we see two terms here that are worth of mention. The first one is phi of t, and the other one is the first derivative of the phi of t with respect to time. And we refer to as the phi of t as the instantaneous phase deviation. And the first derivative with respect to time, we refer to it as the instantaneous frequency deviation of our carrier signal. And we have another definition of change in omega, in which case we see that the maximum change in omega is going to be given by the change in the instantaneous frequency minus that of the angular frequency of the carrier. The maximum value is going to give us what is now referred to as the maximum or peak radiant frequency deviation of an accommodated signal. And now we jump to the definition of each of these two modulation methods, that is the phase and the frequency. And we say that in PM or phase modulation, we define the instantaneous phase deviation of the carrier as being proportional to the message signal, and this is defined by equation 4.6. What you observe in equation 4.6 is that we are saying that this is a direct proportional, or that the phase of the carrier is directly proportional to the message signal itself, and with constant or proportionality being Kp, and we refer to Kp as the phase deviation constant with the units of radians per unit of message signal. And in FM, we define instantaneous frequency deviation of the carrier as being proportional to the message signal. And as we have mentioned already, is that we define the instantaneous frequency deviation as the first order derivative of y of t with respect to time, and that would give you the constant of proportionality being kf, and the which is now relating to the message signal. And therefore, what that gives us is that if we are now to integrate both sides of equation 4.7 with respect to time, we are going to end up with the equation 4.8 that defines the phase of the message, which is phi of t, that is dependent on time, multiplied by the constant of proportionality, that is the instantaneous frequency deviation constant, kf, and therefore relates with now the message, that is the integral of the message with respect to time. Of course, the same applies, that the units for kf is radians per second per unit of mt. And then, of course, we notice that change, that we have an addition of per second in comparison to what we had at equation 4.6. And we say that that phi of t naught is the initial phase of the angle at time is equals to t naught, and it is usually assumed that t naught is going to be minus infinity, and in that case, again, this is always assumed to be equals to 0. And therefore, having defined these two constants, kp and kf, we can define the angle modulated signal first in terms of phase modulation, where we are saying that the phase, remember this was the phase, was represented by phi of t. We have replaced that with the constant of proportionality, kp, and the message signal itself. And again, the definition for the Argon modulated wave, that is in the frequency modulation, is going to be defined by the phase of t that we have said that is represented by the constant of proportionality kf, which is the frequency constant deviation, and of course multiplied with the integral of the message with respect to time. Now, if you recall how we defined the instantaneous frequency omega I, which we said is given by d theta t dt, and therefore we have defined theta as this component for the FM, and omega c of t plus kp m of t for the PM. Then this is theta of t for PM. Therefore, we can definitely say that if you differentiate this with respect to time, then we are going to end up with equation 4.11 and 4.12, because this becomes constant of with respect to constant. This is not supposed to be a bracket, it's supposed to be t. So we are going, when you differentiate with respect to time, this goes, and we have omega c, and this becomes the first derivative of mt with respect to time, and we have that. And similarly, we are able to get, if we differentiate this with respect to time, of course, we want to differentiate only this aspect, not including that. We are going to end up with omega c, and then when you differentiate this, you simply remove the integral. This integral goes, and that we end up with kf omega c plus kf m of t, and that is how we define the instantaneous frequency for phase modulated and frequency modulated waves. And how we conclude those derivations is to state that in phase modulation, the instantaneous frequency omega I varies linearly with the derivative of the modulating signal. As you can see there, the modulating signal is the message signal. And in frequency modulation, we say that the instantaneous frequency omega I varies linearly with the modulating signal. And now we jump to the Fourier spectra of Argon modulated signals. And we say now that an Argon modulated carrier can be represented in the exponential form by writing equations 4.1, which I have written it here, in terms of the complex exponential, whereby we say that we know that this is the real part of a complex exponential. Therefore, we can say that if you are to use the Euler's formula, we would simply say that ej omega c of t is equivalent, or rather, this should have been, anyway, this is fine because if you break this down using the Euler's formula, it will give you cos, which is the real part, and the sine, which is the complex part. So not the complex, but the imaginary part. And therefore, if we take the real part of this, which I have done in the second step, I simply leave out the imaginary part, and I pick the real part, which is the A cos omega c of t. And before we did this bit, we simply first split up this exponent, which is zeta of t being equals to omega c of t plus phi of t, and there is j outside here. Therefore, when you break this part and then you take the real part, you end up with a cos omega c of t, and again, which is now multiplied with this other part, which has a j, because there were going to be j omega c of t plus j phi of t. Therefore, when you break this down again in the complex exponential form, it is going to give you what looks like this. And before we go too much, I just observe that here we are breaking this term using the power series. So we are breaking this term instead of using the Euler's formula, like I had alluded to at this stage. You are breaking this one using the power series, and we say that when you break this in terms of power series, it's going to give you a series that takes that form. And at some point, we can decide to ignore the upper powers of j, and we only deal with 1 plus j phi of t. And therefore, when we multiply, we do that multiplication, which is the one I'm doing at this stage. Then we end up, and we are still interested in picking only the real part of the entire equation. We will see that there is this multiplication and this multiplication, which after you do the multiplication, we are going to end up with equation 414, which simply starts with cos omega c of t minus phi sin omega c of t, etc. So this is the equation that we have just tried to see how it comes about. It just observe two items. First and foremost, we are breaking up the j omega c part using the Euler's equation, and then the ej omega z phi, sorry, ej phi of t, we are bringing it using the power series, and we know the the higher power components. We are only left with 1 plus j phi of t, and when you do the multiplication and leaving out the complex, the imaginary parts, we end up with equation 414. And this modulation simply leads us to one important conclusion, that the Argon modulated signal consists of one unmodulated carrier, which is represented by this term. This is not touched by the message signal, and then plus other unmodulated carriers, which again having higher powers of phi of t, and therefore what we are saying here is that an angle modulated signal, message signal, is not related to the message signal which is or the spectrum of the message signal in any simple way, and therefore becomes quite different from what we saw in amplitude modulated version, which we saw that it was simply directly related by simple translation, as I stated earlier. Now, from equation 4 and 4 that we have just derived right here, we can make an important discovery that if the maximum value of phi of t, the frequency, the phase change, the maximum value of this term is, if it is far much less than 1, then we end up with an important realization that we can ignore still these higher power terms, and we end up with the modulated wave x or x of t being approximately equals to a cos omega ct minus a phi of t sin omega ct. And this kind of Argon modulation, in which we have ignored the higher power components of phi of t, then this is the one that we refer to as the narrowband Argon modulated signal. And it is represented by equation 4 and 7, whereby we said that phi of t, if you recall, phi of t for a phase modulated signal, we say is equals to kp m of t. Therefore, when you replace this phi of t with this value, we end up with this equation right here. And therefore, we are saying that the angle, the narrowband, rather, on the other hand, we are done with the narrowband phase modulated wave, but on the other hand, which is the FM, we said that the phi of t is given by kf integral from minus infinity to time t of m lambda d lambda, and therefore when you replace this in this equation 416, what we end up with is the narrowband version of the frequency modulated wave as illustrated in equation 418. So further, equation 416 has additional items that we are able to capture. First thing is that we observe that the narrowband Argon modulated signal contains two terms. One term is an unmodulated carrier, which is represented by a cos omega ct, then plus an additional term in which phi of t, which we have already said is a function of mt multiplies by phase shifted carrier, which is shifted with 90 degrees or pi over 2. And this multiplication generates a pair of sidebands. And if phi of t has a bandwidth of WB, then the bandwidth of the narrowband Argon modulated signal is going to be twice WB. And this one reminds us of how we were able to find the bandwidth of amplitude modulated signal.